Let's now put everything together into one curve sketching menu of the process we can go through when we want to sketch a curve. So things we look out for, because obviously we're just going to be given an equation of a curve and we want to know, okay, what's this thing look like? Now all the ideas from the curve sketching still apply. So just because we know calculus, we don't ignore the others. So we still want to look for things like points of discontinuity. Bottom of the fraction can't equal 0, that sort of thing. Because they will create asymptotes. So we're looking for those sorts of things as well. So then we've got the function, but what we now know with calculus was that the stationary points are going to occur when the first derivative is equal to 0. So that's our first point of investigation. Let's go and find some turning points. Does it turn? Then we go and classify them. So we know it's maximum when we found our stationary and it's concave down, and minimum when it's concave up. If they ask me, or if I'm still not sure what it's going to look like, I'll investigate and look for points of inflection. And that's when the second derivative equals 0 and there's a change in concavity. And as I mentioned yesterday, then the third derivative is a useful tool for that. But as with the first derivative, as with the second derivative, you can always draw up a table of values if the function is difficult to differentiate. And by the way, you can use the first derivative to determine if it's a point of inflection as well. Because if you've got a curve that goes increasing, stationary, increasing, it's got to be a horizontal point of inflection. It's the only thing it could be. So you can use the first derivative to find inflection points as well. We know, right? So if we're unsure, where does the curve exist? Well, we know the curve's going up if the first derivative is positive, and sometimes we can look at derivatives and go, well, hang on, this is always going to be positive. Maybe we've got x squared on the square root of x plus 3. Well, we know the square root's going to be positive. We know x squared is going to be positive. So this derivative is always positive, no matter what the x is. So I know it's always increasing. Similarly, it'll always be decreasing if the derivative is less than 0. Concavity, second derivative greater than 0, we've got an idea about the shape of the curve. We know it's concave up and concave down if it's less than 0. So all these tools can be used, not only just to classify stationary points, but if we're unsure what the curve's looking like at a particular point, we can investigate and see what's the concavity look like and things like that. So, basic cubic, let's do it. X cubed minus 6x squared plus 9x minus 5. And the setting out here is what I want to emphasize. Again, don't be lazy. Explain what you're doing. Let's find our tools then. So we're going to need the first derivative, we're going to need the second derivative, and let's assume we want to find inflection points. So I need our third derivative. Now straight away, I see the third derivative is a constant number 6. So any possible inflection point will be an inflection point. Okay, stationary points, tell them what you're doing. Stationary points occur when the derivative is equal to 0. So I'm trying to find them, that's what I want to solve, and we get 1 or 3. All right, let's go classify them. When it's 1, we get negative 6, concave down. So 1 minus 1. And again, just be careful where you substitute to get your y value. It's so easy to make a mistake and sub it into the derivative rather than the function, and amazingly all the y values then turn out to be 0 because they're stationary points. Okay, x equals 3. It's now positive, so 3 minus 5. And let's find that possible inflection point. As I say, in this case we actually know it will be, but we're still looking for possibilities. 6x minus 12 equals 0, so it's at x equals 2. And as I say, let's just emphasize it. Yep. Well, we know the third derivative is 6. 6 is not equal to 0. So there must be some change happening. I didn't write it there. Bad. Naughty. Should have written, therefore there is a change in cavities. What does that mean? Okay, let's draw it. Let's put all that information on. So 1 minus 1 is the turning point. There's another one down there. 3 minus 5. There's the inflection point. At this stage, it looks like we're drawing a straight line. There's my y-intercept, negative 5. My x-intercept, I'm not going to worry about. I will only find x-intercepts if they're easy to find. Now, they gave me a cubic. Do I want to waste time trying to factorise that? What was the equation? Let me go back. Does 1 go into it? So 5's prime. Does minus 1 or minus 5? I'm not sure, because as I said, I didn't bother finding it. But I'm not going to waste time. I'll show you how I get away with that too. Alright? So, Here we go. Remember, we're not playing dot to dots. So, zigzag. Excellent. Just decided. Yeah, look, it'll go up there somewhere. It'll cut, but I don't care. Yeah. Unless they specifically ask you to say, and label the intercepts or something like that.
Ask you to just sketch it, you could just...
Sure. Because I'm saying that continues. That's what the arrow's telling me. That keeps going. Okay. So there we go. There's our procedure for curve sketching.